Swayam Prabha. Digital India. Educated India.
So a mesh can have things inside, but for typing, let's assume that it's a hollow mesh. When I said that there's nothing inside, I wanted to say that it's not a volumetric mesh. It's a surface mesh. So things are only on the surface. We are only representing the surface. Let's take a look at some of the mesh data structures. Some of the very primitive data structures to represent a mesh do it with the help of just arrays of the coordinates of the vertices and the facets. So, for example, over here, you could say that let me have every vertex being stored as x, y, z triple, and then every face is then three times each vertex. So you have 9 numbers associated with every vertex. Let me also point my cursor to the data structure I'm referring to. So look at the face set data structure. Here, a face is defined as a collection of 3 vertices. Every vertex has 3 coordinates, x, y, z. That's my definition of a face. And how do I represent the mesh? A mesh is just a collection of faces. So you could think of this mesh being if there are n faces in this mesh, then I could say that I could store it with a n by 9 matrix, where every row is a triangle face. Looks like a horrible data structure because the topology is completely lost. There is no graph information here. All I'm storing is a collection of faces separately. And sometimes this is referred to as a triangle soup. A triangle soup. I can write that here. Known as a triangle soup. Right? So you have a collection of faces. It's a triangle heap or soup, and there is no connectivity information. And unfortunately, it is also difficult to create a connectivity information out of it. Can somebody tell me why is it difficult to create connectivity information in the first case, face set? Remember, every vertex is stored as XYZ coordinates, where these XYZ coordinates are floating point values. So who will tell me why it is difficult to create the underlying graph of the mesh? Any thoughts?
Because we don't have information of whether a particular vertex of even we don't know the valency of each vertex.
Yes, you don't know the valency of each vertex, and more importantly, you don't know which vertex is connected to which other vertex. In between the triangles. Within a triangle, yes, you know that there are 3 vertices and they have to be connected to each other. It's a complete graph for a triangle. But between 2 triangles, you don't know what is the connectivity, which edge is shared, which vertices are shared. You don't know that. So that has to be built. But building that, yeah, go ahead, please.
We could find out, like say if any of the faces have some common points.
Yes, but how would you figure out the common points? You must do floating point comparisons to figure out common points.
Yes.
Right.
Okay.
So yeah. So what I'm referring to the fact is that in order to establish the graph, you must do floating point comparison, and those are bad. That's all I meant. You can of course do floating point comparison. People do that. Float A equals to float B, but that's a dangerous comparison because it's susceptible to numerical errors and whatnot. So Integer comparisons are better, but in here there is no integer comparison possible because I haven't stored that information. So this is good for a few things. For example, it is good for rendering, where some of you, if you are familiar with the graphics processing units or the graphics card in your computer, the graphics card loves this data structure because the graphics card is very, very parallel in nature. It has a lot many processors and it wants to process the mesh triangle by triangle. So what it needs is just a collection of triangles flattened out so that it can quickly do a parallel computation and display it on the screen. So this data structure is very fast for rendering, displaying the mesh. But for any other task like traversal of the mesh or doing some mesh processing, it's probably best avoided. And there are certain better data structures if you want to do mesh processing. The next in the line is the indexed space set, in which we try to sort of store some topological information, and that information is usually sufficient to quickly build the topology, but the topology is not explicitly stored here. So let me tell you what this data structure is. In this data structure, a face is, and by the way, on these slides, when you see a green box, that's the type, and adjacent to it are is an example of how it is stored as an array. So the type or the structure here is in green. So a face is stored as a, okay, I think there is slight problem here, which I will correct later. But a face here is a collection of vertices. In this case, 3 I think I did a mistake, little bit of a mistake here, but a face here is a collection of 3 vertex indices. If you look at on the right hand side, there is a vertex array and there is a faces array. The vertex array just lists all the vertices. So it's a m by 3 array where you have m vertices and 3 coordinates for each vertex. And a face is then defined as 3 vertex indices connected to each other. So now you can immediately see that a vertex may appear in multiple faces, multiple rows of the faces array. And that's precisely is the little topological information that is that we have here. So because it is indexed, this is known as an indexed face set. Everybody clear on why it is a better structure? Because, and as a bonus, you save on space. You basically split your faces into a vertex array and a faces array, and the faces array is only using integers to index into the vertex array. Is it clear to all? I will fix this the one in green. There is no edge ref in this case. It has to be vertex indices. But I hope you understand that. Any quick questions here? It's a very simple data structure, just a slight extension of the face set. But still, you still don't have the explicit topology. That is still missing. So if you want to know which triangle is adjacent to which triangle, you will still have to parse through this faces array and figure out which two vertices are common in 2 triangles. So there would be exactly 2 triangles. Sorry, there would be exactly 2 triangles in this faces array that will have 2 vertex indices in common. So you will have to search through it. Is that right? So that's my index face set. Good for certain purposes. In fact, the GPU also likes this data structure. It can take this one. But what I'm coming to is a edge-based data structure, and there are two prime candidates here. One is known as a winged edge data structure, and there is a more recent one which is known as the half edge data structure, which is the de facto standard when you want to do mesh processing. So you have you have a mesh represented in terms of a vertex, face, and edge. So edges are central to this data structure. That's why it is known as a half edge. And what you do is that you don't store an edge as an edge. You split an edge into two half edges. So what you look here in the diagram is one half edge going in one direction, and the opposite half edge, known as E opposite, going in the other direction. So let's take a look at the edge data structure. The edge data structure has a vertex reference, which points to an index or a reference pointer from the vertex array. Then it has a face reference, which points to a face reference. We'll talk about the face structure. It has a half edge reference to the next and the previous. Maybe it's best if I draw it. So what are the components? A previous half edge, next half edge, and opposite half edge, and some data associated with the edge. The face has a half edge reference and some data. The vertex has a half edge reference and its position, of course, and the data. So let me quickly draw and then sort of make it a little more clearer. All right. So half edge. Data structure. Right. So you have one half edge, let's call it E, and another half edge, let's call it E opposite. That's my basic representation. Then that's my edge, right? So I have a vertex for which this E edge, the E half edge is outgoing. Similarly, I have another vertex here. That's the origin vertex for E opposite. So if I call it V0 and V1, then for V0, I will store a pointer to E. And then if I want to reach out to V1, I would say E and then fetch E opposite from E, because E has a pointer to E opposite. And then E opposite will have its source vertex V1. So I can reach out to that. Basically, these data structures are for traversal and modification of meshes. And traversal is the, sort of being able to traverse through the mesh is one of the main ideas behind it. You have looked at data structures for numbers, like trees, linked lists. So you can think about, this is like a doubly linked list for meshes, right? And let's say you have another vertex here, V2. So then you have this half edge here, and then another half edge connecting this one, then another here, then another here, and then I can draw a little more. And anytime you have a question, please do not hesitate, ask. Okay, so every face is then defined by a cyclic collection of edges. And whenever I represent meshes, there is this notion of handedness or orientation of a triangle. So let's quickly say what is orientation of a triangle. So everybody is familiar with the right hand thumb rule, studied in physics, maybe in class 9th or 10th. You have a triangle here. The triangle is oriented in this is counterclockwise orientation, counterclockwise. And if it is counterclockwise, then the normal vector is given by the right hand thumb rule. So that's the normal vector of this triangle, where this orientation is counterclockwise or anti-clockwise. So usually we take counterclockwise as positive, and that's the standard. You can always do clockwise orientation, nothing wrong in that, but you need to be consistent. If one triangle, if you want to keep counterclockwise, then make sure all triangles in your mesh are counterclockwise oriented. So if this has vertices A, B, C, so then if I specify the vertices of this triangle, I would say A connected to B connected to C. Actually, any cyclic permutation of this is a valid counterclockwise orientation. So I could also say B connected to C connected to A, or C connected to A connected to B is also. These are all counterclockwise. How can I make it clockwise? Just swap any two adjacent vertices and it will become clockwise. So if I flip AB, then it becomes BAC. So BAC, you can check it rotates, it turns clockwise. And then any cyclic permutation of BAC is also a clockwise. I will just place dots here. So coming back to this, so this is clear, right? The orientation part is clear.
Yes, sir. Sir, what is the context behind the orientation? Like,
Vignesh, I can't hear you. Can you please a bit louder?
Sir, what is the context behind talking about orientation in this, like, while explaining about the opposite?
Yeah, I'm coming to that. But for now, assume that for now, let me, if I say that I have a mesh, and then let me draw a 2D shape here like this, which is composed of instead of triangles, I have these polylines, and let me just split this into two polylines. So that's my polyline representation. Every line has to have a normal vector. So there is something known as orientation of all these elements, facet elements. And these are consistently oriented facets if the normals of all the facets are consistent. If I have a normal inside and some of them are outside, that's inconsistent. Because a lot of algorithm will depend on consistent orientation. I would want to make sure that my mesh triangles or my mesh facets are consistently oriented. And while I'm explaining this data structure to you, I want to explain to you how this data structure can keep your facets consistently oriented, which is a very which could be a requirement for an algorithm, for a mesh processing algorithm, or even display. Right? So if it is inconsistently oriented, some of the display algorithms might just remove the facets from display without you noticing. This is known as backface culling. And then you would see that, oh, my mesh has holes in it, where actually there are no holes. It's just the display algorithms are fine-tuned, are optimized to remove any back-facing triangles. So in this particular case, this guy is back-facing. This guy is back-facing. So these are called back-facing. And these algorithms just remove the back-facing algorithms because you don't want to display back-facing triangles because that means that they are not visible to you in some algorithms. Let me not get into details of that because I'll run out of time today. But for now, just take it that orientation is required. So if I come back to this data structure, my anti-clockwise orientation of facets is like this. And then you will notice that these edges, the edge E and its cyclic neighbors all form a clockwise orientation. Take the next half edge, which I'm drawing in red here. that's the opposite. And then if I take the cycles of this one, this face, these are also arranged in a cyclic fashion. And then you will notice that I can keep on going, and it's always a cyclic order. That becomes, you know, a very handy thing when I'm representing these meshes. And that's true always in all the meshes. So isn't it a nice thing that I get for free here, that all the half edges in a facet are oriented in a counterclockwise fashion, and that helps me maintain the orientation of all the facets. So is it okay, Vignesh?
Yes, sir. Yes, sir. Thank you.
Right? Yeah. So you have these counterclockwise oriented facets, and so what does this data structure has? The edge data structure has a pointer to the edge. Sorry, it is the edge, so it doesn't need a pointer to it. It has a pointer to E opposite, so that it can go to the next facet by jumping to E opposite. Then you know, this guy is called E next, because it is the next in the counterclockwise fashion, and it has a pointer to E previous, which is the previous edge to E. So E next and E previous. So these are the three edge pointers that are contained in this edge, and these help in navigating the mesh. For example, I want to navigate around the vertex V0, and I'll again draw it here. This is E, and I want to navigate around this this vertex. How do I do that? And by the way, navigating around a vertex is known as one ring traversal. Okay, it's known as a ring. This is a ring, one ring. So it's known as a one ring traversal. So how could I? So now you know that I can jump from edge to edge. How do I do this one ring traversal? It's very easy. I have now the half edge data structure is not tied to triangles. It may have polygonal facets as well, right? So how could I do this traversal? You could imagine that, you know, you will have to jump through opposite, previous, and so, right? So maybe I can, for sake of saving time, let me just, you know, tell you what it is, and I'll draw the opposite edges in blue here. So these are the edges which I want to traverse. These outgoing edges is I want to traverse, and I think this is yeah. Okay, so right. So how do I do that? How do I do this one ring traversal? One ring traversal can be done. So you are given E. So from E, you jump to, and let me not use the arrow here because that could be confusing here. I'll just use comma here. So from E, you go to E previous, opposite, and let's call it E1. Let's call it E0. Okay. That's going to be messy with this notation, so I'll just erase E0. So you do E, you jump to E previous, and from E previous get its opposite. And once you have E1, you do the same. You go E1 to E1 previous, and then E1 actually E1 previous opposite, and similarly this should be E1 previous opposite, but I hope you get the idea. Okay, I don't want to mess it up. Do you understand that you go from E to E previous and then opposite on that E previous? Because I'm sort of using this shorthand notation here. There are some assignments here, but if you want, I can explicitly write it up for you guys. And then you keep doing it until you reach E. Until you reach E. Until reach E. So it's a while loop. So until you get back the pointer E, you keep on doing E previous, E to E previous to E opposite. And then that's going to do one ring traversal. Similarly, you can do one ring traversal for facets as well. That is, traverse all the sides of a face instead of traversing edges of a vertex. Okay. And then you can, of course, with every half edge, you have a pointer to its face, the left face. So you could always see that this face, this face is always to the left of E, to the left of E previous, and to the left of E next. So for all the half edges of this face is always onto the left. It is never onto the right because we followed a consistent orientation. So if it is counterclockwise oriented, the face, let's call it the face F. Let's call it the face F. The face F is always onto the left of E. So I could just I could grab a pointer to that, and then that's what we have it in the data structure. Okay, let me quickly jump back to these slides to show you what more we have in the data structure.